29th, so this is isomeric, and they're looking for esters, structural and stereoisomer. So you gotta take care of whether there's cis and trans, whether there's optical isomer, there's your chiral carbons or not. If methanoic acid, alright, so there's a condition there. Methanoic acid is one of the two reactants, so I'll get something methanoate. So there's your 1 carbon acid, so you have 4 carbon alcohol. Okay, think about it, 4 carbon alcohol. I have a lot of space down there, so I'll move down there. So 29. What do I have? This is your acid. I'll get the 4 carbon alcohol. 1, 2, 3, 4. Okay, so straight chain. What else could I have? 3 carbon. If I have 3 carbon, then I can branch it out here. What else can I have? I can put my methyl there, but I can put my methyl there as well. And that is chiral. This is not chiral because these are CH3 and CH3, but this is CH3 and this is CH2, CH3. So that is chiral, so that will give me 2. That is 1, that is 2, that is 3 and 4. Can I get another one? There's a tertiary. So there's a tertiary alcohol there. If I think about drawing the alcohol, I hope you can see that. So there's a chiral there, and there is no other chiral center. Okay, so these are all possible isomers of a 4 carbon alcohol. Alright, so I have 2 there because of the presence of the chiral center there. So they'll give me 2 non-superimposable mirror images. So that will actually add on to the stereoisomer because they asked us to consider that and also stereoisomers. Alright, so I got 5. I counted 5 altogether. If I have methanoic acid as the other acid component, so each of these has the methanoate as the other component, so I have 4 carbon to play with other isomeric. I have 4 carbon to isomerize, okay, for the alcohol bit. So question 30, you have this compound X. It's got unbranched carbon chain. So unbranched means it is straight chain. So an aqueous solution of X has an approximate pH of 3. So that tells us is acidic. Compound Y is a secondary alcohol. So it's a 3 carbon alcohol and it's a secondary alcohol. So I'm thinking of this. This has got 3 hydrogen, 4, 5, 6, 7, 8. C3H8O. This is Y. It's got to be, okay. Propan-2O, 3 carbon alcohol. C3H8O if you count from this skeletal formula, which you should be able to do at ease. The pH 3, I sort of thought that it would be quite strong, but clearly there is a weak acid because there's an organic acid. Alright, we are not talking about nitrogen or phosphorus or sulfur, so these are just acids that are from carbon. So those are carboxylic acid, pretty weak. And we have a carboxylic acid and alcohol and a little corn sulfuric acid. That tells us that we are doing condensation reaction because we are forming esters. Alright, the type of reaction is called condensation. It's covered in introductory organic chemistry. Yeah? Hang on. It's a 4 carbon carboxylic acid and it's unbranched. So we are looking at X. We are looking at X being a straight chain acid. 1, 2, 3, 4. And your Y is propan-2O, secondary alcohol. So what is the structural formula of Z, which is the ester? Okay, so when you form an ester in a condensation reaction, as I mentioned, condensation, the acid would lose the OH and the alcohol will lose the H. Then they come together. that will give you the ester, and then they will kick out water. The H and the OH kick out the water. This is called condensation. So there's your ester. So they've decided to, so there are two way of looking at it. Your CH3 twice is definitely from your alcohol bit. So that is definitely from your alcohol bit. And you have two sites that have CH3 twice, and that's incorrect because you have an unbranched. You have an unbranched carboxylic acid. So only one of them is branched. I can tell you D is wrong because this shows branching on both sides. Alright. I can tell you C is wrong because both sides show straight chain. And that's incorrect. We know one of them is branched. We know the alcohol is branched. We know the carboxylic acid is straight. This was wrong because both of them were branched. These were wrong because both of them were straight chain. How about this one? This one has got branch on one side, but when you see this CO2, so that is your acid. That is your alcohol. Can you see your alcohol is straight chain? So that means this is wrong because your alcohol is straight chain. Alright? Alcohol is branch. Secondary alcohol. Alright, probably shouldn't write too much into that. But your secondary alcohol is branch. Your secondary alcohol here is straight chain. Therefore, we are looking at these. Your straight chain, 1, 2, 3, 4. 4 carbon acid. Your alcohol, 1, 2, 3, and it is branch. So we're looking at option B and not A. Finally, we reach this section B type of questions. So you should be very familiar with how we approach section B type of question. We always tackle option number 2 first, because by logic, if 2 is incorrect, you're left with one option. If 2 is correct, then you check number 1. And if number 1 is incorrect, you're left with this option. And if 1 is correct, then you go for the next one and you check number 3. And if 3 is correct, then this is the answer. If 3 is incorrect, then you're left with this. Alright? So a bit of logical thinking, I guess. This has been quite a tricky paper so far, so you can see I've been working quite slow so that not to make mistakes here and there. So always read the video details, video descriptions, because I do make mistakes, and I rely on the students and the viewers to tell me when I make mistakes. So when I go slower, I can cut down my mistakes. But obviously going slower would mean that it would take much longer time in the real exam, and that is not ideal when you cannot finish the exam paper, yeah? Anyway, I'm doing my thought process here. In reality, you're probably doing all this, you know, your brain is working at like what, quad core or more than quad core processor. You should be able to work faster than me in the real deal, okay? So question 31, if I check number 2 first. So what do we have? We have an organic compound in the gaseous state. You have excess of oxygen. You get carbon dioxide and nitrogen, not water, because all of these contain nitrogen gas. Nitrogen atom. So I give you nitrogen molecule among the products. These are gases. So we are doing gas combustion analysis. Alright. Because they all measure the same temperature and pressure, they will have the same molar volume. Therefore, mole ratio is equal to volume ratio. What can I say? So if I have that, if I have CO2 and I have J, CO2 and N2, if I have 10 cm cube of that, if I check option 2 first, if I have 10 cm cube of that, and how much carbon dioxide would I get? Well, I have 2 carbon. In 1 molecule of J, I have 2 carbon. Therefore, I will get 2 times 10, which is 20, because 2 CO2, because you will have 2 carbon from there. They will give you 2 CO2. So 1 of J will give me 2 of CO2 because it's got 2 carbon. So 2 times 10. Mole ratio equal to volume ratio. Okay. 1 mole of J will give me half mole of N2 because it's got 1 nitrogen atom. So it'll be half times 10, which will be 5. these are volumes, so 10 cm3 of these will give me 20 cm3 of these and 5 cm3 of these, so 2 is correct. Alright, how about 1? If I have 1 molecule of J, I have 2 carbon atoms, so again I'll get 2 times 10, which is 20 cm3. How about nitrogen? So in 1 molecule of J, I have 2 nitrogen atoms. That will give me 1 nitrogen molecule because there's 2 nitrogen atoms there. So one of these will give me 1 of N2. 1 times 10 is 10 cm3, not 5 cm3. But in this experiment, you only get 5 cm3 of nitrogen. 2 is correct, 1 is incorrect. You're left with option C. I can move on. Alright, you can of course check for the other one, but by right you should be able to just move on. If I just very quickly check for the other one, 1 mole of these, 1 of these will give me 2 CO2, so that's 2 times 10, which is 20. And again, 1 of these will have 1 nitrogen. So to get N2, you need half, because there's 2 nitrogen atoms there. You only have 1 nitrogen atom, so you need to half the volume. Alright, half. So you get 5 there, which is exactly what you have been given. So that's why option 3 is also correct. 32. So you have this electronic configuration as shown. And then these are elements, and these are the compound. I can tell you it's probably easier if you work out what element it is. 2 and 6. 2 and 6, that's group 6, that's oxygen. And then 2 at 1, that is sodium. 2 at 7, that is chlorine. Okay. Well, Y2X, so you have Na2O. That is giant ionic structure. That is your oxide of 3rd period chemistry. We talk about liquid state, that is molten. Molten ionic compound has free ions, so you can conduct electricity. YZ is going to be NaCl. Same deal, also giant ionic structure. So you have free ions in the molten state, so you can conduct electricity. Z2X is going to be Cl2O. Cl2O is a simple molecular structure, so you have between nonmetal and nonmetal. Actually, Cl2O looks like this. It's got 2 bond pair and 2 lone pair around the oxygen. So there is a 104 degree. Some people like to call it 104.5. Perfectly fine. That is because you have 2 lone pair. They repel more than bond pair, and that in turn repel more than just bond pair. Again, this brings back to what I said earlier. Valence shell electron pair repulsion theory, which is actually very, very important as part of your structure and bonding. So that is just a simple molecule there. Only 1 and 2 are correct, so that's option B. Question 33. So in this question, all gases can be assumed to behave ideally. So when you heat a mixture of nitrogen and oxygen gas in a sealed container, you reach equilibrium, dynamic equilibrium, right? You repeat the experiment at the same temperature using the same initial amount, but at a much higher pressure. So the change here is changing to a higher pressure, but same temperature, same initial amount. So which statement about the second experiment at higher pressure are correct? So first of all, pressure can affect equilibrium position, but only if you count that there is a difference in the number of gaseous molecules on the left and on the right. Here you have 1 mole of N2, here 1 mole of O2. So you have 2 moles of gases on the left hand side. Here you have 2 moles of NO on the right hand side. Also 2 moles of gas on the right hand side. In a theory paper, you will say there are equal number of moles of gases on the left and on the right. Okay, therefore changing pressure will not affect the equilibrium of this particular equilibrium because there are equal number of moles of gases on both sides of the equilibrium. So the composition of equilibrium mixture does not change, is precisely correct, and this is the reason. Okay, counting the moles of gases on both sides and coming to term that they are equal. So changing pressure will not affect your equilibrium position, it will not affect your equilibrium yield, it will not affect your equilibrium composition. At higher pressure, you put pressure on gaseous reactants or gaseous product, you put pressure on them, you make them closer together. That's why there are more particles per unit volume, because you force them, you squeeze them closer together. And in that sense, they will collide more frequently. That's why they collide more frequently and they'll give you a faster rate of reaction and higher pressure. Alright, so 1 is also correct. And in fact, 3 is also correct, where I just talked about when they are closer together, when there are more particles per unit volume, you get more collision per second. Alright, but your Maxwell-Boltzmann energy distribution is unchanged, because changing pressure or changing concentration does not change your molecular distribution, does not change the distribution of molecular energy. Only temperature can change your energy distribution. Alright, so not pressure, not concentration, because they only affect collision frequency. As a result, more particles colliding per unit volume since they are closer together. So all 3 are correct. That's just option A. 34, you have an ethanol burner used to heat up water. This is your classic calorimetry kind of experiment. So your heat transfer is minus mc delta T. So m is the mass of water. As you know, these are of your surrounding, which is our solution, and water makes up the majority of our solution. So m is the mass of water, that's correct. Delta T is change in temperature of the water, which is of the surrounding. C is specific heat capacity of the water. Everything is of the solution, of the surrounding, of the water. Okay, so only 1 and 2 are correctly described. Option B. Question 35 is the first ionization energy of 20 successive elements in the periodic table. Hope you can see that the highest one are going to be the noble gases, so group 18. So we are essentially going down the group. That's why you see this is higher than this and this is higher than this. It goes all the way down there because you are filling in a new shell which is further away from the nucleus, and the valence electrons are therefore more shielded because they are more shielded by the inner shell electrons. This is your group 2 and 13. Your first drop is due to filling in the P subshell. This is the P block. This is the S block. In fact, the P block ranges from here all the way to here. P1, P2, P3, P4, P5, P6. So this is between P3 and P4. When you go to P4, because your P orbitals, you have 3 of them degenerate, 3 in the P orbital, so there's your P3, and then you have P4, parallel, 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 Hans first rule, fill with parallel spin first, and then you pair them up. Okay, so this is your P4, this is your group 15, this is your group 16. Alright, so that is your 15 to 16. That account for the second drop because your paired electron will repel more than the unpaired electrons. So it's slightly easier to remove from the paired electrons because you are removing this unfavorable repulsion. That's why there's a slight drop there. Increase again all the way up to the noble gas, which going down the group, obviously you have more shells. That's why it's easier to remove the valence electron as you go down the group due to increased shielding because you have more filled inner shell. And it goes all the way back down to 1, 2, 13, and then the effect becomes less pronounced as you go down the group because these become less and less important as you are further and further away from the nucleus after all. Anyway, they're asking for which statements are correct. So D and L contain 2 electrons in the outer shell. Where is D? D is that, so D is indeed group 2, and L is indeed group 2 as well. So group 2 means they have 2 electrons in their outer shells. So 2 is correct. B, J, and R. B, J, and R. B is group 18, J is group 18, R is group 18. So they're all noble gases. So that is correct. G and O have a half-filled p subshell. So it's saying there's P3, saying there's group 15. G and O. This is G. G. So G is group 15. How about O? O is also group 15. Alright, so G and O are group 15. So that is correct. G and O are group 15. They have a half-filled p subshell, which is P3. So all 3 of them are correct. Which properties increase in that sequence? HCl going to HBr going to HI. When you compare bond length, well, if I have number 2, bigger halogen atom, therefore longer bond. So in fact, as the halogen gets bigger, your covalent bond gets longer. So that's correct. And then number 1, as your covalent bond gets longer, as HX is longer, we have weaker HX bond. So weaker HX bond mean easier to break. If they are easier to break, they become less stable to heat. Less stable to heat will mean your thermal stability decreases. So that means 1 is incorrect. We're just looking at option C, which is 2 and 3. Right? Ease of oxidation. How easy to be oxidized? Well, you can think of this as iodine minus 1, Br minus 1, Cl minus 1. Even back in your GCSE or IGCSE or O level, you would have known that Ki, which is iodine minus 1, very good reducing agent. Alright, as a halide, Ki, which is I minus 1, which is iodine minus 1, very good reducing agent, like to be oxidized. How easy to be oxidized? Very easy, because very good reducing agent. So that's why C is also cover 2 and 3. 37. Which statement about this structure are correct? Well, the C12 ring is not planar. That is correct because they are all carbon sp3. The carbon has 4 bond pair. You don't show the hydrogen, but there's 2 hydrogen, 2 hydrogen, there, and there. There's 1 hydrogen there. On each of the brominated carbon, you also have 1 hydrogen. Okay, so that is your tetrahedral. 109 degree with 4 bond pair and 0 non pair. So they are not planar, they are tetrahedral. Empirical formula. So work out the molecular formula, which is the total number of atoms in the molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 2 hydrogen, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1 hydrogen. Carbon form 4 bond, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18. And then you have Br. You have Br2, 4, and 6. So you have empirical formula, which is the simplest ratio of the atoms in a compound. So 12 divided by 6 is 2, 18 divided by 6 is 3, B6 divided by 6 is just 1. C2H3Br is correct for the empirical formula. 6 chiral carbon atoms. So let's think about this. So chiral carbon, we have a carbon bonded to 4 different groups. Alright. So if I imagine cutting down that thing in the middle, okay, because I'm looking at this carbon. If I'm here, I will have one different, and then I will have this thing versus this thing, which are different, because there will be 2 Br, there will be 3 Br. Okay, because on one side versus the other side, because I'm looking at my carbon with the Br, not the CH2, because the CH2 obviously it's got 2 hydrogen, it cannot be chiral. So I'm looking at the carbon with the Br. On one side I will have, well, something with 2 Br and something with 3 Br. They are different, alright? So that would definitely be my chiral carbon, because there's also a hydrogen, alright? But then that is just looking at one of the Br. That means if I actually look at each and every other Br, I will also have a chiral carbon here, 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 and here, because wherever I look, it's pretty much the same situation. If I cut it there, I will have 3 bromine and 2 bromine on one side, and therefore I will have chiral carbon on each of the blue colored carbon. So I have 6 chiral carbon atoms altogether. So there's just 1, 2, and 3 all being correct. 38, this is also asking about chiral carbon. This is, so they say 3 of the carbon atoms are labeled 1, 2, and 3. So we are just looking at the label. We are just looking at the label carbon atoms. We are looking for chiral. Let's look for option 2 first. You can cross out option 2. This is a carbon sp2, 120 degree, trigonal planar, because it's an alkene chemistry. You know hybridization for alkene versus alkane. This carbon has got 1, 2, and 3 bonded to this carbon, and it's got 1 sigma, 2 sigma, and 3 sigma. So there's your 3 bond pair, but 0 lone pair, because this carbon has formed 1, 2, 3, and 4. Okay, it has formed 4 covalent bonds altogether. So that thing causes you to be trigonal planar, carbon sp2, 120 degree. You can't have chiral carbon when you only have, carbon bonded to 3 different groups. Therefore, only one is correct. That's option D. And 1 is definitely correct, because if you split this molecule into half, this side has alkene, this side has no alkene. Alright? It's got OH, it's got this group that are different. If you look at the group at the bottom, you see these are CH3 and CH3. So this thing cannot be chiral because these 2 groups are the same. 39. So this is the nucleophilic addition mechanism. It's one of the key case study in your A-level chemistry. You can find out all the required A-level chemistry mechanism in the organic chemistry mechanism playlist, amongst the many topical playlists on the AS as well as A-level chemistry contents. Yeah. So this is asking you about what is true about the mechanism. Well, I just told you it's nucleophilic addition. This is saying there is nucleophilic substitution, so clearly you should know that it's not a substitution. You have added 2 things together, you just form 1 thing. If this is a substitution, you will have 2 things come together, you will get 2 things. That is how you define substitution reaction back in introductory organic chemistry under terminologies. Yeah. So therefore, only 1 is correct. And in fact, you know that Na plus Cn minus, fully ionic, versus molecule. If you know this mechanism inside out, you will know that we actually use this as the first nucleophile that attacks the carbonyl of the aldehyde ketones, and then this is the main reactant as the oxy-anion intermediate. Oxy-anion is the intermediate. Negative charge on the oxygen attack this hydrogen, delta plus. It will kick out Cn minus, which regenerate you back the Cn minus from the catalyst. So 40, this is the last question of this paper 1, which hopefully I haven't messed up that much, okay, because I've been going a bit slower. So part 2, this is a ketone. Well, I mean option 2. When you add it with NaBH4, so there's Na plus and BH4 minus, this is a reducing agent. It's got a H minus delivery system, which I hope you can see is pretty much going to go via nucleophilic addition. Alright, and that will give you your secondary alcohol, because this is reduction, where they like to ask you to balance the equation by using this kind of square bracket hydrogen to represent the reducing agent. And of course you need to balance the equation with H2O, either on the left or on the right, depending on the reaction that you are doing. Okay, you should be able to do that if you have seen a couple of theory papers. So 2 is actually correct, because you can reduce ketone to secondary alcohol, propan 2O from propanol. Number 1, I can tell you number 1 is wrong, because that is electron rich. This is ionic. This is called a hydride. This is called lithium aluminum hydride. This is rich in electron. The thing with hydride as a reducing agent is that they are ionic, they are rich in electrons. They cannot, and they will not reduce alkene, because alkenes are electron rich. Alright, so there's the reason there. So 2 is correct, 1 is wrong. Answer must be C. And you know that you can reduce aldehyde back to primary alcohol, where the carbon with the OH is bonded to one other carbon. So 3 is also correct. So that's the end of this paper 1 tutorial.